Hey everyone, in Chemistry 40S and Chemistry 40SH land, welcome to a screencast of what? Unit 5, Lecture 3, more KSP stuff. We're going to learn about Skills 3 and Skills 4. So this is Unit 5, and I got to add my notes here, right? Okay, well, what color shall we use today? What do you think? Anna. There's three Annas. This color, purple. Okay, Anna. So, this is Unit 5. One of you is listening, I hope. Well, I hope all three of you are listening. Unit 5, skill numbers 3 and numbers 4. So this is Lecture 3 in Unit 5. And we just keep going on from where we learned about skills 1 and 2. In skill 3, we're going to quantitatively determine if a precipitate really forms. You know, in those qualitative solubility tables with all those little I's for insoluble, also known as sparingly soluble, and S for soluble, there are all those little ones. Those are all rough ideas. Here we're going to quantitatively say, do we really have enough cation and anion smashing together to fall out of solution? Remember, falling out means to precipitate out of solution, right? So the way we determine that is we calculate something known as QSP, and then we're going to compare QSP to KSP. So get out your booklets, get to the page that is skill number 3, and if you really want to know what page number that is, it is page 10. Okay, page number 10. So let's quantitatively determine if a precipitate really forms. We need, this says need, we need QSP, which has the same form as KSP, except you plug in the instantaneous concentrations in for QSP. So in other words, the concentrations of cation and anion just before the possible precipitation happens. That isn't necessarily the initial concentrations because you're mixing things together. Aqueous solutions, it's all about aqueous solutions here. So there's dilutions that happen. So we're going to like to use the word instantaneous as opposed to initial. So there's three possibilities. If QSP is less than KSP, well, you don't get a precipitate. The system is still unsaturated. If QSP is greater than KSP, you do get a precipitate. And if QSP just equals KSP, you just start to get the precipitate. Okay, so that is our set of conditions. So let's take a look at how this comes into play. So first of all, example 1a, will calcium sulfate precipitate if, and you're given KSP of 2.4 by 10 to minus 5, if you have a solution which is swimming around with 0.0025 moles per liter of calcium 2 plus and 0.03 moles per liter of sulfate. So that is my cation and anion instantaneous concentrations. Is that enough to make a precipitate? So here's my solubility equation. I can get my KSP, calcium 2 plus times SO4 2 minus, which is 2.4 by 10 to minus 5. My QSP, you just take the values that are given. So calcium 2 plus is 0.0025, and the sulfate is 0.03. You multiply them together, and you get 7.5 by 10 to the minus 5. Since QSP is greater than KSP, then a precipitate does result. Okay, this BB, let's just cross that out. That's just for something different. Don't worry about that. Okay, so now let's start fresh, but this time we'll have some 0.0025 molar of the calcium, cation, 2 plus cation, and we start dripping in some sulfate. How much do we need just to get the precipitation to happen? I mean, in example 1a, we had more than enough sulfate for the 0.0025. The 0.03 was more than enough. Maybe we don't want to waste the sulfate. Say your boss is saying, hey, we got to reclaim some calcium from this solution. We don't want calcium ion being in the solution. It's causing some problems with some seashells or something. I don't know, some aquatic life. So we want to get the minimum amount needed. And to do that, you set your QSP equal to your KSP, because when QSP is equal to KSP, you just start to get precipitation. So that's the key. You set your QSP equal to the KSP, which is given 2.4 by 10 to minus 5. So that equals my instantaneous calcium 2 plus concentration times my minimum sulfate. So my minimum sulfate concentration is going to be 2.4 by 10 to the minus 5 divided by 0.0025. So that is 0.0096 molar, which is 9.6 by 10 to the minus 3, which is less than the 0.03. So the MIN stands for minimum. When you think of minimum amounts needed, think of setting QSP equal to the KSP. Okay? So that's what that is all about. Let's go to example 1C. Let's start over again, but this time let's say I had 0.001 molar of sulfate. What will be the minimum amount of calcium ion needed to drip it in? So here I had some sulfate, and the boss says, gee, we got to get sulfate out of there. It's causing problems in the environment. So you're going to drip in some calcium ion to trap that sulfate, make it precipitate. So you set QSP equal to KSP. So my calcium 2 plus is going to be 2.4 by 10 to minus 5 divided by 0.001. So 2.4 by 10 to minus 2 molar. Okay. Let's do a more advanced case here on page 11. Given a KSP of Ag2CrO4 is 1.2 by 10 to minus 12. Will it precipitate? That's a 4 there. Not a 9, but a 4. Will a precipitate form in a solution which has 3.4 by 10 to minus 4 moles per liter of chromate, CrO4 minus, and 4.8 by 10 to minus 5 molar of Ag plus? If I look at the qualitative solubility tables, it tells me that silver chromate will precipitate. But if I don't have enough, then quantitatively it won't, right? There's always a difference between qualitative and quantitative. Quantitative means, yeah, it might. Qualitative means it might. Quantitative means you get the exact numbers, and you can make a better comparison, and you set up the QSP and the KSP, and you see what's going on. So here's my solubility equation. Ag2CrO4 goes to 2 Ag plus CrO4 minus. So my KSP is Ag plus squared times CrO4 minus, which was given as 1.2 by 10 to minus 12. And my QSP is my Ag plus instantaneous squared times my CrO4 minus instantaneous. So it's 4.8 by 10 to minus 5 squared times 3.4 by 10 to minus 4 for my chromate. And I get 7.8 by 10 to minus 13. And then we make the comparison, our since statement. Since QSP is less than KSP, 7.8 by 10 to minus 13 is less than 1.2 by 10 to minus 12, I do not form a precipitate of silver chromate. Doesn't happen. Okay? So an obvious question might be in 2b, or not to be, that is the question. But in 2b, how much Ag plus is needed to start the precipitation? So the chromate was 3.4 by 10 to minus 4. So in other words, we're asking for what's the minimum amount of Ag plus needed to start the precipitation. So Ag plus instantaneous minimum squared times the chromate is 1.2 by 10 to minus 12. So I take 1.2 by 10 to minus 12 divided by 3.4 by 10 to minus 4. I take the square root, and the minimum amount needed is 5.9 by 10 to minus 5. Okay? And let's see, how much did I start with of the Ag plus? 4.8 by 10 to minus 5. So I didn't have enough of the Ag plus to begin with. I needed 1.1 by 10 to minus 5 more to get the precipitate going. Okay, let's try an example 3 together here. Given KSP of cadmium chromate, 5 by 10 to minus 9, will a precipitate form if you've got 2 by 10 to minus 5 molar of cadmium 2 plus and 3 by 10 to minus 7 molar of chromate? Then it says prove it. Okay, my guess is it will. My QSP is going to be my instantaneous concentration of CD2 plus, which is 2 by 10 to the minus 5, times chromate, 3 by 10 to the minus 7. So that's 6 by 10 to the minus 12. And hey, I was wrong. It does not precipitate. Okay. Let's punch it on our calculators and make sure. So I got 2 by 10 to 5 minus times 3 by 10 to 7 minus 6 by 10 to minus 12. So will it form? No. Since QSP is less than KSP, no precipitation results, right? QSP was 6 by 10 to minus 12 is less than 5 by 10 to minus 9. Now, some students get mixed up on this. They say, oh, 6 is more than 5, so QSP is more than KSP. Don't do that. 6 by 10 to minus 12 is a real small number. It's a lot smaller than 5 by 10 to minus 9. 6 by 10 to minus 12 is this, 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 5 by 10 to minus 9 is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, and then I can pad it with zeros, right? So 6 by 10 to minus 12 is less than 5 by 10 to minus 9. Okay, so that was page 11. Now we go to page 12 and to skill number 4, which is needing information from skill number 3. No surprise. The whole idea is QSP greater than KSP. If I mix two solutions together, will a precipitate form? We're talking about the antibiotic aqueous in a then starting to drip into an IV bag containing sugar or salt. We don't want a precipitate to form when we mix those solutions together. So there's practical reasons why we have to know. Sometimes we do want to pour one solution into another. We want a precipitate to form and then filter it out. Maybe it's a pollutant that causes lots of issues in our water supply. We want to find ways to trap it and get rid of it and hide it somewhere, right? The only case we look at in this chapter, we'll just look at equal volumes, okay? Which allows us to do a shortcut. So if you see a mix of two solutions and the two solutions are of unequal volumes, then we aren't going to bother with it. The concentrations can be unequal, and many times are, but we'll just look at the case where the volumes are equal, and we'll look at the case where the two solutions, where there's just two solutions we're mixing together. We aren't going to mix three solutions together at the same time. So the reason why it's a big deal about using equal volumes is it allows us to create a shortcut where our final concentrations of our ions are just 1/2 of what they started with, because you mix equal volumes of things which are essentially water, with just a little bit of ions dancing around in them. And so you got twice as much water, so you're half as concentrated. That's the whole idea behind it. So let's go and look at example 1 here. We have 100 mils of 0.05 molar silver nitrate. Okay, well, we got solution, then obviously, well, we said it's going to be aqueous. And it's mixed with 100 mils of 0.08 molar sodium bromide. Will something precipitate? Well, it's not going to be, it's a double replacement reaction, but it's not going to be sodium nitrates, because nitrates never precipitate, nor do alkali metal ionic compounds. So if anything is going to precipitate, it's going to be silver bromide. And then I could look at a table, or I could just give you a few KSPs. So the KSP of AgBr is given as 5.4 by 10 to the minus 13. Okay, so here's my solubility equation. AgBr solid goes to Ag plus aqueous plus Br minus aqueous. My KSP is Ag plus aqueous times Br minus aqueous, which is 5.4 by 10 to the minus 13. My QSP is my instantaneous concentration of Ag plus times my instantaneous concentration of bromide. And how I get those numbers is my AgBr, my source was silver nitrate. The volumes are equal, 100 mils of silver nitrate, 100 mils of sodium bromide. So you just take the source concentration, 0.05, and divide by 2. That is your instantaneous Ag plus concentration. Similarly for the bromide, I started with 0.08 and take that and divide by 2. So get those numbers, multiply them together, you get 1 by 10 to minus 3, which is a lot more than 5.4 by 10 to minus 13. So yes, precipitation does result when we mix these together of equal volumes. Notice here I'm not asking for the minimum amount needed, I'm just asking, do we get precipitate or not when we mix equal volumes? The answer is we do, and it's silver bromide that precipitates. Okay, let's look at a second example here. We're going to have silver nitrate and ammonium carbonate. Those are both soluble. I know that because I'm talking about volumes of them. 600 mils of 0.4 molar was 600 mils of 0.7 molar of ammonium carbonate. Once I realized that I have 600 mils of one and 600 mils of the other, I don't actually do anything with the number 600. The point is that those numbers are equal. That's why we do that dividing by 2 in the QSP. So silver carbonate, that's not, oh no, if anything's going to precipitate, it would be silver carbonate, right? Ammonium nitrate won't. So sometimes I ask students to write out for practice the OME, the CIE, and the NIE. So you can do that for practice for this one. And then we get to the nitty-gritty here. So the solubility equation, Ag2CO3, which is just the reverse of the net ionic equation, right? Ag2CO3 solid goes to 2Ag plus aqueous plus CO3 2 minus. So my KSP is Ag plus aqueous squared times CO3 2 minus, which is 8.1 by 10 to the minus 12. And my QSP is going to be, well, what was my source of silver nitrate? 0.4. So 0.4 divided by 2, and I'm going to square that. And then the carbonate is 0.7 divided by 2. I get a number which is 1.4 by 10 to the minus 2. And since that QSP is greater than KSP, a lot greater, precipitation results. Okay, let's see, do we have another one here? Okay, so those are two examples of equal volumes. Unequal volumes that I'm going to omit at the moment. So let's go to page 14 and look at something interesting called selective precipitation. I don't really have a skill number for these minor topics that we get to here. So what we have in selective precipitation is a beaker which has a whole bunch of junk in it, right? We call it a slurry, let's say, from we're refining some ore like aluminum oxide or something, so we're heating the living daylights out of it to get refined metal, which we then use to make pots and pans or whatever. So we got a bunch of stuff swimming around, and there's going to be anions in there, but here I want to list some cations. So I got copper 2+, and lead 2+, and cadmium 2+, and iron 2+, tin 2+, zinc 2+, and nickel 2+. So those are all swimming around aqueous in a solution, and now I start to drip in an anion. Okay, so I start to drip in some from, let's say, a burette, which we are going to use in acid-base chemistry. What am I putting in? Some sulfide, S2-. Okay, so you're going to form copper sulfide, lead sulfide, cadmium sulfide, iron sulfide, tin sulfide, zinc sulfide, nickel sulfide, all Roman numeral 2, right? Which one is going to precipitate first? Let's also simplify things, say they all have the same concentrations of these cations. Well, the one that precipitates first is the one with the smallest KSP, right? Because it needs the less amount of the anion to let the QSP match with the KSP. So once the QSP matches to the KSP, it starts to come out. And you'd have to be given the KSP value. So here's a table where they're all given. and you see that the smallest one is the copper sulfide. Copper Roman numeral 2 sulfide. 8 by 10 to the minus 37 is the smallest. So if the boss said, gee, we got to get rid of copper more than any of the others, and I don't have much sulfide, so and I don't have much anion resources, and you'll ask, well, do you got sulfide? And your boss says, yeah, I got a little bit of that, some sodium sulfide, let's say. You say, great, I'm going to drip in some sulfide. It's going to react with the copper first, and I'm going to filter off that copper sulfide. And then after that, the next one I guess would come out would be the lead sulfide, right? Because it's 3 by 10 to the minus 28, so that's the next smallest one. And the one that would hang around the longest in this example would have to be the iron sulfide with the 8 by 10 to the minus 19. Okay, if we wanted to mathematically find out how much sulfide would be needed to get the precipitation happening, so I'm going to go here. My KSP is going to be equal 8 by 10 to the minus 37. So the minimum amount of sulfide, knowing that the Cu2 plus is 1 by 10 to the minus 5, would be 8 by 10 to the minus 32. Okay, this one here, I don't care about that. So that is an example of selective precipitation. So you might expect 1 or 2 questions on an assignment or a test about that. Now, here's something which is actually related to hard water. If some of you have ever been in the Canadian Shield, or lucky enough to have a cottage or visit someone who has a place around there, you'll notice that the water supply may be a bit scummy. You have some calcium deposits. You might need a water softener. And it all has to do with this common ion effect, and I'll let you watch a YouTube video or read up about hard water versus soft water in different parts of Canada. But it is related to a common ion effect, which is not being able to dissolve as much of a solute in a solution which already has one of the components of the solute in it compared to dissolving in pure, unadulterated, lovely water. Okay, so here's an example. We got silver chloride, and if I use pure water as a solvent, well, I dissolve a little bit, not much, but I dissolve a little bit of silver chloride into my Ag plus and my Cl minus. Now, instead, if I was dissolving that silver chloride into a solution which already had some silver nitrate in it, then I have a common ion, right? Ag plus is the common ion because it is present in both Ag plus of AgCl goes to Ag plus Cl minus, and also the AgNO3, right? AgNO3 goes to Ag plus NO3 minus. Now this isn't common. You know, they talk about tables of common polyatomic ions and things like this. You know, ones you use a lot. That's not the definition of the word common here. The definition of the word common here is that you see it in 2 different equations. And the common ion you see in both the equations, pure water and dissolving, silver nitrate dissolving to Ag plus NO3 minus, which dissolves easily. It's a strong electrolyte. And then the AgCl goes to Ag plus Cl minus, doesn't dissolve as easily. So Ag plus is the common ion, and if you have it there, you can dissolve even less of the Ag plus. Another way to think of it is starting with the AgCl and then dumping in the AgNO3. That will cause more AgCl to precipitate out. Equilibrium will shift to the left, and that's from our friend Le Chatelier's principle, right? So that is an example of a common ion effect. So your solvent, what's in your solvent, is an important thing to deal with. Okay, now as I scroll quickly through here, I see on page 15 there's worksheets, and on 16 there's more, and I'm going to sign bits and pieces of these worksheets. This chapter is a bit on the short side, which is good. It's got worksheet Ferdinand. It's another one here. page 18. Page 18 is our solubility chart, if you didn't know that already. And you can use this for any quiz, assignment, test, etc. And I didn't like this thing about slightly soluble, the P, so I switched all the P's with I's. So I means sparingly soluble, and S means soluble, and then some general rules and paragraphs on 18, and then there's some more worksheets as we go through the rest of the pages in the booklet. So that is the story, and that is Unit 5 on solubility. So you're going to get lots of practice starting right now. Check your EDSB for various assignments.